two projects. In this video, we are going to explain the project Mushroom Classification using Transfer Learning. Introduction. The primary goal of this project is to develop a robust classification system for mushrooms, categorizing them as either edible or non-edible. With the rising interest in harvesting and the potential risks associated with misidentification, a reliable classification tool is essential for ensuring safety in mushroom consumption. So, the project addresses the critical issue of accurately distinguishing between edible and non edible mushrooms. Edible refers to mushrooms that are safe for consumption and are not known to cause harm or toxicity when eaten, and non edible mushrooms are those that are either poisonous, toxic, or inedible due to their taste, texture, or potential adverse effects on health when ingested. So, misidentification can lead to severe health consequences, including poisoning or even fatality. Leveraging deep learning techniques, we aim to provide a dependable solution to this problem. Historically, mushroom classification has heavily relied on manual identification techniques, which often involve intricate visual examination and reference to field guides. However, these methods are labor intensive, time consuming, and prone to errors, particularly for inexperienced individuals. Moreover, the vast diversity of mushroom species complicates accurate identification. So, the proposed system involves the utilization of deep learning algorithms trained on extensive datasets of mushroom images and associated metadata. By leveraging advanced image processing techniques and pattern recognition, the system aims to automate the classification process, offering a faster, more accurate, and scalable solution compared to traditional methods. So, deep learning, especially through transfer learning, revolutionizes mushroom classification. Transfer learning allows models to leverage knowledge gained from solving one problem and applying it to a different but related problem, significantly enhancing accuracy and efficiency. Moreover, deep learning models continuously improve through iterative learning, adapting to new species and variations, thereby enhancing the safety and accessibility of mushroom foraging and consumption. Object of the project. So, as I mentioned earlier, the primary objective of the project is to create a robust classification system capable of accurately distinguishing between edible and non edible mushrooms. This is crucial for ensuring the safety of individuals who harvest and consume mushrooms, as misidentification can lead to severe health consequences, including poisoning or fatality. By implementing various deep learning algorithms, we aim to develop a reliable tool that can effectively categorize mushrooms based on their edibility. And the project utilizes a diverse range of deep learning algorithms, including transfer learning models such as VGG16, MobileNet, ResNet 50, Inception V3, Exception, DenseNet 16, and ResNet 101, as well as LeeNet, EfficientNet, and CNN architectures. These algorithms are chosen for their ability to extract meaningful features from mushroom images and learn intricate patterns necessary for accurate classification. By leveraging these state of the art models, we aim to improve the system's performance and robustness. And to evaluate the performance of the implemented algorithms, various evaluation metrics such as accuracy, precision, recall, and F1 score are employed. By comparing the performance of different algorithms using these metrics, we aim to identify the most effective approach for mushroom classification. And the beneficiaries of this project include foragers, consumers, and researchers involved in mushroom related activities. Foragers and consumers will benefit from having a reliable tool for quickly identifying edible and non edible mushrooms, thereby reducing the risk of accidental ingestion of toxic species. Researchers can also utilize the developed classification system for further studies on mushroom biodiversity, ecology, and conservation. Overall, the project aims to enhance the safety and accessibility of mushroom foraging and consumption for a wide range of stakeholders. Requirements needed to execute this project are software requirements. Software needed is Anaconda. Primary language used is Python. Front-end framework used is Flask. Backend framework used is Jupyter Notebook. Database used is SQLite 3. And front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working modules of flow of work. So the first step is important required packages. In this step, we import necessary Python libraries including NumPy, Pandas, and TensorFlow's Keras module. These packages provide essential functionalities for data manipulation, numerical computations, and building deep learning models, which are crucial for our mushroom classification project. The second step is importing the dataset. Here we load a dataset containing various mushroom images, which will serve as the basis for training our classification model. This dataset consists of images representing different types of mushrooms, both edible and non edible, essential for teaching the model to distinguish between the two categories accurately. The third step is data pre-processing. So using TensorFlow's image data generator, we pre-process the image data by rescaling pixel values to a range between 0 and 1. This pre-processing step ensures that the model receives standardized input data, which helps improve training efficiency and performance. Additionally, we generate batches of augmented images to feed into the model during training. Augmented images are artificially modified versions of the original images created by applying random transformations such as rotation, scaling, shifting, flipping, and brightness adjustments. These augmentations help diversify the training data, exposing the model to a wider range of variations and enhancing its ability to generalize to unseen data. The next step is training and building the models. Here we employ various pre-trained deep learning models such as VGG16, MobileNet, ResNet 50, Inception v3, Exception, DenseNet 16, ResNet 101, and LeeNet, EfficientNet CNN architectures for mushroom classification. These models serve as powerful feature extractors, capturing intricate patterns from the input images. We fine tune these models on our mushroom dataset to tailor them specifically for our classification task, ensuring optimal performance. And in the next step, using Flask framework along with SQLite for user sign-up and sign-in functionalities, we develop a front-end interface to interact with the mushroom classification system. This interface allows users to upload images of mushrooms and receive classification results indicating whether the mushroom is edible or non-edible. The integration of SQLite enables user management, ensuring secure access to the system. Finally, users can input mushroom images through the front-end interface and the system processes these images using the trained classification model. Based on the learned patterns, the system outputs predictions indicating whether the input mushroom is edible or non-edible, providing valuable information for users engaging in mushroom foraging and consumption. Now we'll understand about the algorithms used. So first we'll see the transfer learning models. So transfer learning is a machine learning technique where knowledge from a pre-trained model on one task is transferred to a new related task, often resulting in improved performance with less data. So the first algorithm built is VGG16. It is a deep neural network with 16 layers containing 138 million parameters. Despite its size, its appeal lies in its simplicity. The architecture utilizes small convolution filters, ReLU activation functions, and 3 by 3 receptive fields, maintaining a constant input size of 224 by 224. It employs pooling layers to reduce dimensionality and fully connected layers for classification, making it effective for tasks like image classification. The next algorithm built is MobileNet. So, MobileNet, TensorFlow's mobile computer vision model, revolutionizes deep learning by utilizing depthwise separable convolutions, reducing parameters significantly compared to traditional networks. This architecture allows for lightweight yet powerful models, ideal for resource constrained environments like mobile devices. Its efficiency in both speed and memory usage makes MobileNet well suited for the mushroom classification project, where quick inference and minimal computational resources are essential. The next one is ResNet 50. So it is a deep neural network featuring a unique bottleneck design, optimizing parameter usage and training speed. Its architecture consists of one by one convolutions, reducing computational complexity while maintaining effectiveness. With its ability to efficiently learn intricate features through its deep structure, ResNet 50 is well suited for tasks like mushroom classification, where capturing subtle visual patterns is crucial for accurate categorization, making it a suitable choice for this project. The next algorithm built is Inception V3. So, Inception V3, a member of the Inception family, utilizes innovative techniques such as label smoothing, factorized 7 by 7 convolutions, and an auxiliary classifier to enhance its performance. This architecture efficiently learns and generalizes features while reducing computational cost and mitigating overfitting. With its ability to propagate label information effectively and capture nuanced features, Inception V3 is well suited for the mushroom classification project, ensuring accurate categorization and robust performance. The next algorithm built is Exception. So it is a convolutional neural network architecture known for its use of depthwise separable convolutions, which efficiently combine spatial and depthwise convolutions to reduce computational complexity while preserving representational power. This design allows Exception to achieve state of the art performance with fewer parameters, making it well suited for resource constrained environments like mobile devices or scenarios where computational efficiency is crucial, such as the mushroom classification project. The next one is DenseNet 169. So it is a CNN architecture again renowned for its dense connectivity pattern, enabling robust feature reuse and gradient propagation throughout the network. With 169 layers, it offers improved accuracy and representation compared to its predecessors. DenseNet 169's ability to efficiently capture complex patterns make it ideal for tasks like mushroom classification, where nuanced visual features are essential for accurate categorization. The next one is ResNet 101. So it is a deep residual neural network architecture composed of 101 layers designed to address the challenge of training very deep networks. It utilizes residual learning where shortcut connections bypass several layers, alleviating the vanishing gradient problem and facilitating the training of deeper models. With its robust architecture and pre-trained weights available from the ImageNet dataset, ResNet 101 excels in image recognition tasks, making it suitable for projects like mushroom classification, where deep learning models are essential for accurate categorization. Now we'll discuss about the DL architectures built, which are not transfer learning models. So the first one is LeanIt. LeanIt consists of multiple layers of convolutional and pooling operations followed by fully connected layers. LeanIt's design allows it to extract hierarchical features from input images, making it effective for tasks like image classification. While it may not be as deep or complex as modern architectures, LeanIt's simplicity and efficiency make it suitable for applications where computational resources are limited or for serving as a baseline model in projects like mushroom classification, where accurate image recognition is paramount. The next algorithm built is EfficientNet. So, EfficientNet is a family of convolutional neural network architectures known for their efficiency in terms of both computational resources and performance. They achieve this efficiency through a compound scaling method that uniformly scales network width, depth, and resolution. This allows efficient net models to achieve state of the art performance with fewer parameters and lower computational requirements compared to traditional architectures. For the mushroom classification project, where computational efficiency is crucial, EfficientNet's ability to deliver high accuracy with reduced resource usage makes it an ideal choice. And the last algorithm built is CNN, that is Convolutional Neural Network. So, CNNs are deep learning models specifically designed for processing structured grid like data such as images. They consist of multiple layers, including convolutional pooling and fully connected layers. CNNs operate by convolving input images with learnable filters to extract meaningful features, which are then progressively aggregated and processed through subsequent layers for classification and regression tasks. In this mushroom classification project, CNNs are well suited due to their ability to automatically learn and extract relevant features from mushroom images, enabling accurate classification based on visual characteristics. Now we'll see the comparison graphs. So this bar graph consists of subplots, each representing the accuracy, recall, precision, and F1 scores of different algorithms. In this graph on x-axis, I have algorithm names, and on y-axis, I have respective scores, accuracy, recall, precision, and F1 scores. So accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. Recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. Precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. And F1 score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So, the algorithm which is best performing in all the performance metrics will be used for classifications. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is dataset folder in which I have edible and non-edible mushroom images on which we'll train the models. This is models folder in which I have model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is Notebook Jupyter source file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file Explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command is used to execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a login link, click on it. Here we have to give our credentials, username and password, and click on login button to sign in. And if we are new to the system, we have to register ourselves first. Click on sign up button. Fill in these details and click on register button to sign up. As I'm already a member, I'm clicking on the sign in link. I'm giving my credentials here and click on login button. So it has redirected us to the classifications page. So here we have to upload any mushroom image and the application will classify it as either edible or non-edible from the image. Click on choose file button. So from sample images folder, I'm selecting this image and click on open. The image is loaded. Now click on upload button. So this is the uploaded image of mushroom. And here we can see the classification that is edible. So the application has classified the uploaded mushroom image as edible. We'll try again. Click on try again button. Click on choose file button. So this time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So this is the uploaded mushroom image and here we can see the classification that is edible again. So the application has classified the mushroom as edible. So we can consume this mushroom. Click on try again link. Click on choose file button. We'll try with another image. This time I'm selecting this one and click on open. The image is loaded. Now click on upload button. This is the uploaded mushroom image, and here we can see this mushroom is inedible, which means we cannot consume this mushroom. We'll try again. Click on try again button. Choose file. This time I'm uploading this one and click on open. The image is loaded. Now click on upload button. This is the uploaded mushroom image, and here we can see the classification that is edible again. So in this way we can upload any mushroom image and can get the classifications if it is edible or non-edible. Now click on sign out. So the conclusion here is the project has effectively met its goals and objectives, resulting in the creation of a dependable mushroom classification system. This signifies the successful implementation of the project. Multiple algorithms were explored and built during the project, including VGG16, MobileNet, ResNet 50, Inception V3, Exception, DenseNet 16, ResNet 101, etc., demonstrating superior performance in mushroom classification. Extensive testing using Flask ensured the system's functionality and reliability, focusing on seamless integration of input image. This phase validated the robustness and effectiveness of the system in handling user interactions, guaranteeing that users can upload images and receive accurate classifications as either edible or non-edible mushrooms. So the project's beneficiaries include foragers, consumers, and researchers who can now rely on a dependable tool for mushroom classification. Moving forward, there is an ample scope for scalability, integration with mobile applications, and expansion into other domains requiring image classification, thereby paving the way for future advancements and applications of the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.